What we have done so far is shown that the free market, under the assumptions of the competitive model, generates Pareto optimal allocations, which means that there is no role for the government to intervene just to maximize efficiency. Nevertheless, for reasons that we're going to see later in the course, the government needs to intervene in the market sometimes, for example, by introducing taxes or trade restrictions. What I want to do in the last section of this unit is to give you tools to analyze what is the size of the inefficiency that is introduced by different government policies. In order to do that, we need to define this concept or tool called deadweight loss, which we are going to denote by DWL. And in order to do that, let me just remind you of a concept. We're going to denote by SS optimal and alpha optimal the solution to the surplus or social surplus maximization problem over all feasible allocations. In other words, alpha opt is the allocation that generates the maximum social surplus over all feasible allocations, and SS optimal is the value of the social surplus at such an allocation. We know, by the way, by the first welfare theorem, that the free market, without any restrictions, we generate an allocation that leads to that social surplus. That's what the first welfare theorem basically tells us. Now, given that, now I can define the deadweight loss at any allocation alpha is just equal by the social surplus at the optimal allocation minus the social surplus at the allocation alpha. And let's think of different ways of understanding what this deadweight loss is. One is a measure of inefficiency, or what is the inefficiency at alpha measured in dollars. Notice that SS optimum is the maximum possible social surplus that an allocation can have, a feasible allocation. So necessarily this number is a positive number that only takes a value of 0, its minimum possible value, when the allocation alpha is efficient itself. The other way of thinking about this, if we go back to a result that we proved last unit, is that this is going to be the sum, or a measure of the sum of the utilities over all consumers at the optimal allocation, whatever they get at an optimal allocation, minus the sum over all consumers at the allocation alpha. And if you remember the results from last section, we can also rewrite this as the difference between two terms, the sum over all benefits of whatever the consumers get at the optimum allocation minus the sum of the cost of producing whatever is produced by every firm at an optimal allocation, and that subtracted minus the same thing, this difference between total benefits and total cost at the allocation alpha, that we're going to denote by this. So these are different ways of thinking about what the deadweight loss means. But in essence, the key thing to keep in mind is that it's a measure of inefficiency. Now, the previous formulas can be applied to compute the deadweight loss in any situation that you may find yourself in. But it turns out that under some circumstances that are actually quite common in applications, the deadweight loss has a nice graphical characterization that makes the computations much easier. And in particular, suppose that, or assume that for any aggregate quantity Q that is produced is allocated efficiently among producers and consumers. What I mean by that is that whatever the level of units that are produced by the market, the production is allocated across firms, so it's produced in the cheapest possible way, and allocated across consumers, so the consumers with the largest marginal benefit for those units get the units. In that case, the graphical there is a very nice graphical interpretation for the deadweight loss that I'm about to show you. So this is our standard diagram. This is the aggregate marginal cost curve as a function of Q that we studied in the previous unit. This is the aggregate marginal benefit curve in the Q unit. And remember, for any Q, this curve is telling you what is the benefit of an additional unit for the group, and here is what is the benefit of what is the cost of producing an additional unit in the cheapest possible social way. So we know in this diagram that Q star is here, and we know that the social surplus at Q star is this, which will be the optimum. Sorry, just to be consistent with the notation, let me call that optimum. Now what happens if we produce a quantity, let's say like this one, that is less than Q star? Well, in that case, the social surplus is only this trapezoid and what do we have? That the deadweight loss at that allocation will be this. Okay? Now we can do a similar analysis for what happens if we produce a level Q greater than Q star. In that particular case, let me bring this line up, the total social cost is going to be the area under this aggregate marginal curve. The marginal benefit is going to be, the sum of the benefits is going to be the area under this curve. So what we're going to have is the deadweight loss is going to be this area. Let me call this Q hard up, and let me call this one Q low. Note for purposes of intuition an interesting difference between the deadweight loss on the left and the deadweight loss on the right. In this case, there is a deadweight loss because there are units that could have been produced for which the marginal benefits exceed the marginal cost. In contrast, in this region, there is a deadweight loss because the last few units that get produced have a marginal cost that exceeds their marginal benefit. So here, there is too little production, and here is too much production, excess production in some sense. One interesting property of the deadweight loss that I want you to observe is that it increases non-linearly and often approximately with the square of deviations between Q and Q optimal. Okay, this should be optimal there. Let's see why that is the case. So compare the following situations. We have our aggregate marginal benefit curve, our aggregate marginal cost curve. This is the optimal amount. And I'm going to do another diagram here that basically measures the size of the deadweight loss as a function of what gets produced. Okay? And compare the following situations. A situation in which there is a little bit of underproduction, or a lot of underproduction, or a little bit of overproduction, or a lot of overproduction. Okay? So in this case, the deadweight loss is this. It's the deadweight loss of a little bit underproduction, and this is the deadweight loss of a lot of underproduction. Notice that the deadweight loss is the area of a triangle, and therefore it's going to increase with the square of this distance. So if you were to draw how that increases, it increases something like this. It's initially very small marginal increases, but then progressively every additional unit of deviation from the optimality increases at ever larger rates. And for the same reason, the same thing is true here. So we have this nonlinear increase. In other words, if you're going to deviate from optimality, the first tiny deviation is not very costly, but once you are deviating a lot and you're sitting on a sizable deadweight loss, further and further marginal deviations from optimality become progressively more costly.